Hello, welcome to this lesson of our study of integral equations, and this is our first lesson. Okay, so if you have not subscribed to the channel, kindly subscribe to support the channel as well. Okay, all right, let's start. So, introduction to integral equation. So when you say an integral equation is an equation in which an unknown function. Okay, so this unknown function here is very, very important. Okay, that's why I've underlined it. Unknown function appears under one or more signs of integrations. Okay, so let's say you have an equation something blah 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 equals, let's say something then plus something, or let's say integral of something. Okay, be u of t dt, let's say something times that, and you are asked to your task here is to find u of t. Since u of t is under this integral sign, then this whole equation becomes an integral equation. Okay, so let's go ahead and look at the general form of an integral equation. Okay, all right, so the general form of an integral equation is given by this. Okay, the first one, which says y of x equals, okay, this y of x equals some f of x plus lambda times the integral from a to b of the function k of xt times y of t dt. Okay, so here you can see that what we don't know here, the unknown function has been labeled. Okay, so let me try to explain to you all these terms. Okay, so y of x that I've written in the first one here is known as the unknown function. That is what we want to find. Okay, and f of x is the free or forcing term, this one, and with that it is always known. Okay, it is being given and is known as well. Okay, and then this lambda here is an investigative parameter, and this lambda, what it does is it shows you the variation of the solution. Okay, if you allow the lambda to vary. Okay, let's say if we make lambda, let's say 2, what will happen to that? If you make lambda to a -1, what will happen to that? Actually, lambda is a real number. Okay, so it varies. I hope you understand. And a and b already, we know that when you have an integration, then these a and b's will definitely be the limits of integrations. Okay, and we have k of st, which is a function of both s and t, and that is what we call the kernel. And the kernel is always also known, and it's continuous about the limits. Okay, it should be continuous about the limits. I hope you understand this. So these are just the name of the terms inside the general form of an integral equation. Okay, so let's go ahead and look at the classification of an integral equation and probably take some examples and work on them. Okay, so how do you classify an integral equation? Classification of IE. I'll be using IE a lot in this to signify or identify integral equations. Okay, so we can first of all classify an integral equation according to structure. So this one is what? By structure. Okay, if you could see, I just wrote by structure here. Okay, and that is, so what we are coming to do here is classifying an integral equation considering the form or its structure. Okay, so under the structure we have what we call the Fredom's integral equation, we have the Volterra's integral equation. Okay, now with the Fredom's integral equation, you can see that these two equations, I've written two examples here, and you can see with this and this, you can see that they are almost the same, but if you check them very clearly, let's see. This is sorry, there is a mistake here. This shouldn't be f of x, it should be y of x. Okay, it should be actually y of x. Okay, that is it. Now you can see that this y of x here that we are talking about here is the same as this y of x. Okay, let's check them one after the other. Okay, let me clean this so that you understand what I'm trying to say here. I want us to go through them one by one so that you know the difference. This half s cubed is the same as half s cubed. In front of the integral equation, they both have 1 there. Now let's look at the lower limits. The lower limit of this is 0. The lower limit of this is also 0. Now look at the upper limit of this is 1, but this is x. And you can see that apart from that, all of them are the same. So this 1 here and then x are not the same. So this and this, they are not the same. Now this constitutes the difference between Volterra's integral equation and Fredom's integral equation. Okay, I hope I can clean the things I did. Okay, sorry. So here, what I mean is that with Fredom's integral equation, what happens is that the limits of integration are just constants. Okay, so a and b are both constants. They are just numbers. Okay, and with the limits of integration of Volterra's integral equation, the upper limit b is a function of x. Here is equal to x. Okay, so here you can see that a is equal to 1 and b is equal to 0. So with the Volterra's integral equation, the limits is a function of x, and particularly in this course we'll be dealing with a function of x where b is equal to x. That is all that we'll be dealing with. Okay, but we have other forms of Volterra's integral equation. Okay, but know that when the limit, the upper limit is a function of x, then you have Volterra's integral equation. In other words, b equals a function of x, and then a is still a constant. Alright, I hope you understand. So with the Fredoms, you have a, b being constant, and with Volterra's, b is a function of s. Let's move on to classification by kind. Okay, so here too, the by kind actually also depends on, you can see that with the structure, it depends on the limits, okay, of integration. I'm talking about the Fredoms and Volterra's. Now with the kind, it depends on the unknown function. Okay, the unknown functions are the y of something. Okay, so now you can see that for the first kind of integral equation, by kind, you can see that for the first kind, the unknown function only appears under the integral sign. So you can see here that there is no y of anything throughout the whole of this equation except under the integral sign. Okay, so this is what you call the integral equation of the first kind. Now when it comes to the second kind, the unknown function appears under the integral sign and also elsewhere. Okay, so when the integral equation you are having, when it has the unknown function being appearing at or under the integral sign and any other place, then you have a second kind of integral equation. But when it appears under, or when it appears only under the integral sign, then you have a first kind of integral equations. Okay, so you can see that here it depends, the kind classification, it depends on the position or where you can find the unknown function. Okay, so when it is only under the integral sign, you have first kind, and when it appears under the integral sign and any other place or elsewhere, then you have a second kind of integral equation. I hope you understand this. Okay, all right, so let's go to the homogeneity. Okay, so classification by homogeneity, homogeneity property. I hope you understand this. This is very, very cool. Now you can see that if I'm to compare this to the general form of integral equation, then this is an unknown function, but there's no a free term or forcing term here. The f of x that we're having in our general form, it was something like y of x equals f of x plus something lambda something like that. But you can see that for this particular type that we have under the homogeneous, f of x is actually equal to 0. Okay, f of x here equals 0. So when you have f of x being equal to 0 in an integral equation, then when it comes to the homogeneity property, it means that it's homogeneous. But when the f of x is not equal to 0, so here if I'm comparing the non-homogeneous aspects to the general form, you can see that f of x is equal to half s cubed. Okay, this is our f of x. So if I compare this one to the general one, this is our f of x. So when f of x, or when you have another function of x inside the integral equation apart from y of x, or apart from the unknown function that you are looking for, then you have a non-homogeneous. But when you have just y of something going to something and there's no f of x in it, then you have a homogeneous, this one. But when f of x is present, or you have a function of x present apart from the integral equation or the integral sign there, then you have a non-homogeneous integral equation. I hope I make sense here. All right, so let's go to the other ones. So by linearity property. So you can also classify integral equation according to their linear, or being it linear or not. Okay, so here if I want to know that a function is, or an integral equation is linear, then what I have to do is I have to make sure that first of all the integral equation that you are doing, it has how do you call it, the unknown function has a degree of 1. That is the first thing. So here you can see that the unknown function y of x here has a degree of 1, and y of t inside the integral equation, integral sign, also has a degree of 1. So they are just of degree 1, and we are okay. And also, if you have to consider when it doesn't happen in its, or it doesn't exist in its transcendental functions. Okay, I mean it doesn't exist as len of something, a natural logarithm of it. Okay, it doesn't exist as sine of it. So you can see that for the first one, the linear aspect, the degree of y of x is just 1, and the degree of y of t is also 1, and there's no sine of it, and there's no cos of it, or len of it, like that. Okay, so here this one that you have here is linear. Now when you come to the other one, you can see that the y of x, with the first example, let me talk about the first one, this one. With that one, you can see that y of x has a degree of 1, okay, has degree 1, but y squared of t has a degree of 2, because this is the same as saying y of t. The y squared of t is the same as saying y of t all squared, okay, so the degree of that one is 2. So since the degree is 2, then you don't have or you have a non-linear integral equation with the first one. Now you can see that the second one too, have written it under the non-linear. Okay, I mean this one. Now the y of t has a degree of 1. This one is true, nothing is wrong with it. But when it comes to the y of x, it exists as len of y of x. Okay, so it exists under its transcendental function, meaning len is a transcendental function. Len being a transcendental function makes this whole integral equation a non-linear integral equation. So I hope you understand this. I believe you know about linear equations, or let's say linear, how do you call it, differential equation, the same thing. Okay, so the unknown function, when it exists in it, first of all, it has to have a degree of 1 to be linear, and also does not exist in its transcendental form. Any other thing apart from these things are non-linear, which I have them here. Okay, I hope you are cool. Now let's go to what we call singular integral equation. Now when the integration, let me write something. When the integration is improper, I should have added it is. So when the integration is improper, I mean when you have an improper integration, then you have a singular integral equation. Other than that, you have a non-singular integral equation. Now let's look at this example. Look at this example. You can see that the limit of integration is from 0 to infinity, and this is one of the requirements for an improper integration. Okay, so when you have the limits of the integration, either a or b being equal to plus or minus infinity, then you have a singular integral equation. So here you can see that a is positive infinity, and that is that. Now I could have also have something like this. Here this side, I could have for the a, I could have gotten something like minus infinity, and that one to this whole thing also is an improper integral. Okay, or I could have started like how do you call it, here too, to be like, let's say 1 to negative infinity. So the moment you see an infinity, plus or minus an infinity in one of the limits, then you have an improper integral equation. Okay, so you have an improper integration, that makes it a singular integral equation. Or when the kernel, this is the kernel, any function attached to the y of something or u of something is a kernel. So when the kernel is not continuous within the limits of integration, so I have 1 over x as my kernel. Now within the limits of integration is 0 to 1. Okay, 0 to 1. When I plug in this 0, or let me say when I plug in 0 into this function, it becomes 1 over 0, which does not exist, so it makes it discontinuous. Okay, so when the kernel is not continuous, when it is discontinuous, it means it's not continuous. Okay, so when the kernel is not continuous under the limit of integration, then that also becomes an improper integration. And with this, you also have a singular integral equation. Okay, so once you have these conditions happening, meaning either the limits, one of the limits, or both are infinity, then you have a singular integral equation. Or when the kernel is discontinuous, okay, about the limits of integration, then you have an improper integral, and this makes it what a singular integral equation. Okay, other than that, you have a non-singular integral equation. I hope I make sense here. Okay, so let's pick an example and go through them. The question here is classify the following integral equations with respect to structure. Okay, so you are supposed to classify it according to structure, kind, homogeneity, linearity, and singularity. Okay, so you pick one of the integral equations and go to structure. What kind of structure is it? Or under the structure classifications, what can we say about it? Okay, remember that about the structure we have Fredom's integral equations, and we have Volterra's integral equation. So under the structure, you can say either one of these. Okay, so let's pick the example and go. All right, so you have u of x for the first one. U of x equals integral from 0 to x t squared u squared of t dt. Okay, so we have this. Now let's go to the structure. The structure, we are saying that you can only classify integral equation under structure by either saying this is a Fredom's integral equation or Volterra's integral equation. With the Fredom's integral equation, we are supposed to know that the limits of integrations are constant. Okay, and with the Volterra's integral equation, the upper limit, or the b, is actually a function of x, or is equal to x. Okay, so here you consider the structure depends on the limit, so you come and check about the limits here, 0 and x. So once you have b being equal to x, it means we have what? A Volterra's integral equation. So here is very simple, Volterra's integral equation. You are done. When you go to the kind, we are saying that the kind depends on the existence of the unknown function. Okay, so when the unknown function only exists under the integral sign, then you have a first kind. But when the unknown function under the integral sign and elsewhere, then you have a second kind. Okay, so let's go to here. I have u of x here. This is an unknown function that I don't know. And I have u squared of x. So it means it's existing at two places. One under the integral sign and the other one is elsewhere. So it means we have what? A second kind. So this is very simple, right? Then you go to the homogeneity. When you compare this to a general form of integral equation, would you get an f of x in it? No, because there is nothing like this is u of x equals something, okay? And there's no f of x term here, plus something. And we said that when the f of x is equal to 0, then you have what? Homogeneous. Okay, homogeneous integral equation. I hope I'm making sense here. So this is very simple. Let's go to the other ones. Now, the same question, the linearity. The linearity depends either one of the unknown functions having a power more than what? 1, or a power which is bigger than 1. Okay, so here with a u of x here, its power is 1, but with a u squared of t, that one too we don't know, but its power is 2. So once you have this happening, that the power of the unknown function is more than 1, then we have what? A non-linear integral equation. Okay, with the singularity, you have to consider about the integration. Is it improper? One, the first thing that we talked about was if it is supposed to be improper, then how do you call it? The limit of integration should either be plus or minus infinity, or the kernel should be discontinuous about the limit of integration. Okay, so now let's check about the limit. I have 0 and x, and there's no infinity here, so I'm done with the limit. Now go to the kernel. The kernel is what? T squared. Is t squared discontinuous around this 0 and x? When I put 0 here, I'll have 0 squared, which is 0. It exists. When I put s, I'll get s squared. So any number I put there, I'll square it, and it exists. So it means that there's no way this whole integration will be improper. So it means one is a proper integral, then you have a non-singular, okay? A non-singular integral equation. I hope you understand this. So let's go to the second question and solve it. So I believe you can solve this now. Now let's look at this. The structure depends on what? First of all, I said it depends on the limit. So check the limits. They are both constant. So I have a Fredholm's integral equation. Okay. Now the question is you're supposed to check if the unknown function happens to be at the under the integral sign and elsewhere. Okay, so this time around it is only the u of t that we don't know. Okay, so it means that the unknown function happens to be only under the integrals, and then if this happens, I have what? A first kind integral equation. And I go to the homogeneity property. Is there any term apart from u of x? We don't have u of x here, so it means that if I'm supposed to take this cos x to the other side of the equation, then I'll get 0 equals something. So I have some f of x there because this is there and cos x is also there. When you combine these two, then you get your f of x. Okay, so f of x is somehow equal to minus cos s minus s squared, or you can take this whole right side to the other side of the equation and say something about it. So this is non-homogeneous, okay, because it has the other term present. The f of s is present, the non-homogeneous. And when it comes to the linearity property, is there any degree of u of t? Now the unknown function is only u of t, so you just check u of t. Does it have a degree more than 1? No, because the degree is what? 1. Does it exist in its transcendental state? No, because there's no ln of u of t, or there's no sine of u of t, or cos of u of t, or tangent of u. So it means that this is what? Linear. Okay, we go to the last part, which is the singularity. Is it singular or non-singular? Let's consider about the limit of integration. Is there any infinity in this? No, there are no infinity. So we are done with the first checking of our improper integration. Now let's take the kernel. The kernel is ln of what? Xt. Is this continuous around this? Okay, now let's put t equals 0 or s equals 0 into this. It's s equals 0 actually. Now it will be ln of what? It will give us ln of 0 times t, that will be 0, and ln of 0 does not exist. So it means that this ln of x or ln function does not exist around 0, 1. Okay, so this tells us that this whole integration is improper, and once the integral is improper, you have a singular integral equation. So it means this is singular. Okay, I hope you understood the process. So these are the solutions, or this is the solutions to what we call it, the questions or the examples we went through. Okay, I hope you understand the introduction to integral equation, and stay tuned. Thank you, and subscribe to my channel. Kindly please support my channel, share it to your friends, share it to other people that are doing integral equation course, and keep pushing the channel as well. All right, love you and see you next time.